Written homework for Week 5 Distance Learning. Question 1. In this exercise, we test for evidence that average brain size is larger in football players who have never had a concussion than in football players with a history of concussions. The data are in Football Brain 2, where the variable hip measures brain size as the volume of the hippocampus for each subject. The first part says, define the parameters for this question using appropriate notation. Now, in this case, we first look at the response variable, which was the brain size as a volume of the hippocampus. So this is a quantitative response. So let me write that over here. Response is quantitative. And that tells us, I'll just abbreviate, that tells us that we are dealing with means. Then we look at, are we comparing one group or two groups? And in this case, we are comparing people who never had a concussion with football players with a history of concussions. So we have two groups that we're comparing, and we're comparing means because the response variable was quantitative. So that means that we have two parameters, two population means for this problem. So I'm going to call mine mu1 and mu2. So mu1 would represent the mean brain size for football players who've never had a concussion. So I'll write that down. Mean brain size for football players who've never had a concussion, so with no concussions. And mu2 then is going to be the mean brain size for football players who do have a history of concussions. So mu2 is mean brain size for football players with concussions, or who have had a history of concussions. All right, so now I've defined my parameters. Now, anytime my parameter is a mu and I'm defining it, then the first word that should follow the equal sign is mean, because mu represents a mean something. Okay, similarly, if I'm dealing with proportions, then my parameter would be a p, and the first word to follow the equal sign when I'm defining those would be proportion. Next, we want to write the null and alternative hypotheses in terms of the parameters. So our parameters were mu1 and mu2. So our hypotheses are always written about the population parameters. There should never be any symbols for statistics inside of your hypotheses. So I have two hypotheses that I have to write out, the null hypothesis and the alternative hypothesis. The null hypothesis always has the equal sign. So let's write that one first. So under the null hypothesis, mu1 is going to equal mu2. For the alternative hypothesis, we read the question to get context clues to determine whether the symbol is going to be greater than, less than, or not equal to. So if I look back at my problem, we're looking for evidence that average brain size is larger in players who have not had a concussion than in players with a history of concussion. So larger is keyword for greater than. So my alternative hypothesis is going to be mu1 greater than mu2. The next part says use StatKey to find the value of the relevant sample statistic and write it using correct notation. So in this case, remember we are comparing two means. Our goal is to compare two population means, and our best guess at those population means is going to be the sample means. So the sample statistic that we're interested in when we're comparing two means is going to be x bar 1 minus x bar 2. So let's go over to StatKey, and I'll show you how to pull that up and where to find that on the StatKey output. To analyze this data in StatKey, we're going to do a randomization hypothesis test for a difference in means. So I click on test for difference in means. And next I need to find the data set. This particular data set is actually already loaded in here. If I go to the drop-down menu and I choose brain size for football, no concussion versus concussion, then I've already got the data nicely loaded in there for me. Now I can find the appropriate sample statistic by looking over here where it talks about the original sample. So the appropriate sample statistic for the difference of two means is x bar 1 minus x bar 2, which in this case equals 724.6. So looking at StatKey, we were able to discover that x bar 1 minus x bar 2 is equal to 6459.2 minus 5734.6. And if we do that subtraction, we end up with 724.6. So the correct notation for the sample statistic is this part, the x bar 1 minus x bar 2. And the value of the sample statistic that we're interested in is this part over here, the 724.6. Next, we want to use StatKey to find the p-value for our hypotheses. And we're going to write the p-value here. Now to find the p-value, I'm going to need to generate several thousand samples in my randomization distribution. So I'm just going to click on this generate 1,000 samples a whole bunch of times. Once I've got several thousand samples in here, I look to see where the value of my sample statistic would be. So my sample statistic was 724.6. That's going to fall somewhere around this region here on my plot. This is over on the right-hand side of my plot. So to find the proportion that is more extreme or as extreme as that, I'm going to click on the right tail button. Once I've clicked on right tail, then I enter in the value of my sample statistic, which in my case was 724.6. Once I put that in there, then this little floating bubble up here is the proportion of values that were as extreme or more extreme than my sample statistic. So I use this number to help me find the p-value. So as we saw in StatKey, the one-sided p-value for this test is going to be 0.0005. So I'll write p-value equals 0.0005. And I knew that this was a one-sided test because if you look at the hypotheses, and let me just back up there so you can see what those look like. Here they are. If you look at the alternative hypothesis, it said greater than. So in the alternative, if it says greater than or less than, it's a one-sided test. And if it says not equals to, it's a two-sided test. That comes into play when we're looking for the p-value. The p-value is equal to the proportion that is as extreme or more extreme in a one-sided test, or it's equal to double that proportion in a two-sided test. This was a one-sided test, so I'll write that up here even. One-sided. So our one-sided p-value is going to be equal to 0.0005. Next, we want to interpret the p-value in terms of random chance and in the context of brain size and concussions. So the definition of a p-value is the probability of getting sample results that are as extreme or more extreme than what you got if the null hypothesis is true. In this case, our p-value was 0.0005. So that means that a difference in means that is as large or larger than what we got, remember our difference was 724.6. So we're saying seeing a difference in means that is 724.6 or larger would only occur 5 out of 10,000 times if the null hypothesis is true. So clearly this is very unlikely to occur if the null hypothesis was true. And this gives us lots of evidence against the null hypothesis and in favor of the alternative hypothesis. Finally, we're going to state our conclusion. And always remember that conclusions have two parts and they're written in the context of the problem. So the first part of our conclusion is going to be to reject or fail to reject the null hypothesis. This is based on our p-value. If the p-value is low, lower than alpha, then HO must go, so we would reject. And if the p-value is high, then we keep the guy. In our case, our p-value was really, really, really low. So our p-value was 0.0005. Now, this problem didn't specify a particular alpha. When it doesn't specify alpha, we usually just assume alpha equals 0.05. Clearly, the p-value is really low, much lower than alpha, which means HO must go. So the first part of our conclusion is going to be reject H0. The second part of our conclusion is always about the alternative hypothesis. If we are rejecting the null hypothesis, that means we're concluding that the alternative hypothesis is true. So in this case, the alternative hypothesis, I'll back up and show you real quick. There it is. The alternative hypothesis was that the mean brain size for football players without concussions is larger than the mean brain size for football players who have a history of concussions. Since we rejected the null hypothesis, we're just concluding exactly what the alternative is. Only we always want to write it out. We're not just going to use symbols or try and shortcut anyway. We actually need to write out in words what that alternative is. So if I reject the null hypothesis, that means that we have sufficient evidence for the alternative. So we have sufficient evidence that, and now I'm going to write out that alternative hypothesis, that the mean brain size, whoops, misspelling things here, mean brain size, no, still misspelling things, mean brain size for football players with no concussions is larger than, or you could say greater than, the mean brain size for players with concussions. So it's larger than the mean brain size for players with concussions. All right, so that's it. That's the end of that problem. Let's move on to question 2. The Ignorance Survey, United Kingdom. Exercise 4.113 refers to a survey used to assess the ignorance of the public to global population trends. A similar survey was conducted in the United Kingdom where respondents were asked if they had a university degree. One question asked, in the last 20 years, the proportion of the world population living in extreme poverty has, and 3 choices were provided. 1, increased, 2, remained more or less the same, and 3, decreased. Of the 373 university degree holders, 45 responded with the correct answer, which was decreased. Of the 639 non-degree respondents, 57 responded with the correct answer. We would like to test if the percent of correct answers is significantly different between degree holders and non-degree holders. So first part is going to be to define the parameters again. So when I'm defining the parameters, first I got to figure out what are the parameters and how many parameters do I need to define. To do that, I start by looking at the response variable. What did I measure? What was the outcome here? And I wanted to see whether people could answer this question correctly. Okay, so we're looking at correct answers here. Okay, and correct answer is a categorical type variable. Did they get the question correct? Yes or no? So that's going to be a categorical type variable, and if our response variable is categorical, that means that we're dealing with proportions. Next, I look to see if we're comparing one group or two groups. In this case, we are comparing degree holders and non-degree holders, so I have 2 groups. So that means that for this problem, I'm comparing 2 proportions, and when I'm defining the parameters, I then, of course, need to define 2 proportions. So I'm going to have you could call them P1 and P2. I'm going to call mine PD and PN. PD for degree holders and PN for non-degree holders. So PD, and remember when we're talking about proportions, the very first word that should follow your equal sign here is proportion. So PD would be the proportion of degree holders who answered correctly. So proportion of degree holders who answered correctly. And Pn would be the proportion of non-degree holders who answered correctly. So proportion of non-degree holders, non-degree holders who answered correctly. Okay, so now I've defined my parameters using correct notation. I've given the notation for those parameters and I've defined what they mean. Next, I want to write the null and alternative hypotheses in terms of these parameters. So I have null hypothesis and alternative hypothesis. The symbol that always goes in the null hypothesis is the equal sign. So since I'm comparing two proportions, I would say that PD is equal to Pn. For my alternative hypothesis, then I have to look at the context clues in the question to figure out whether I'm going to use greater than, less than, or not equals to in my alternative. The question said we would like to test if the percent of correct answers is significantly different between degree holders and non-degree holders. So different is keyword for not equals to. So my alternative hypothesis is going to be PD not equal to Pn. Okay, remember that the hypotheses are always written about the population parameters and never about the statistics. So hats and bars and things like that do not belong in the hypotheses. Sometimes I say no headwear in the hypotheses. So that means don't put X bar in there, don't put P hat in there, don't put anything with like extra lines or whatever above the things, because those are not parameters, those are going to be statistics. Next, use StatKey to find the value of the relevant sample statistic and write it using proper notation. And actually in this case, they give us the data right here in the problem. We don't actually need StatKey to find the value of the sample statistic, although we can certainly find it on there as well. One of the kind of confusing things I think about this problem is that because it deals with proportion, you don't need a whole data set to give the data for this survey. All you need is 4 numbers. You need the counts of successes and the total number in each of the 2 different groups, which they give you here. So here it says of the 373 degree holders, 45 responded correctly. Of the 639 non-degree holders, 57 responded with the correct answer. So first, I'm going to look at P hat D. So for degree holders, it says that 45 out of 373 responded correctly. So that's going to be 45 over 373, which is 0.1206. Then I'm going to do the same thing for the non-degree holders. So P hat N is going to be 57 over 639. So 57 over 639 is going to be 0.0892. Now because I'm comparing the 2 proportions, then the appropriate sample statistic is actually the difference in the sample proportions. So that's going to be P hat D minus P hat N. And that would be equal then to 0.1206 minus 0.0892, which equals 0.031. So when it says find the value of the relevant sample statistic, the value is this 0.031. And when it says write it using proper notation, the proper notation for the difference in 2 sample proportions is this, the P hat D minus P hat N. Now we're going to use StatKey to construct a randomization distribution and compute the p-value. So let's head over to StatKey and check that out. To analyze this data in StatKey, I'm going to go into test for difference in proportions because I was comparing 2 proportions. Now, because we're looking at count data, we don't need a whole data set for that. We can just click on the edit data and enter in the values that were given to us in the problem. So if you recall, in the problem, it said that there were 373 degree holders, so that's group 1 size, and of those, 45 responded with the correct answer. Out of the 639 non-degree holders, it says 57 responded with the correct answer. So once I enter in those 4 count data numbers, that's all I really need to do this problem. From here, I can look over here and find my sample statistic value. So we were able to calculate this by hand, but it's also given over here under original sample on the right-hand side. Now I'm going to generate my randomization distribution. Once I've generated a few thousand samples, then I look to see where the value of my sample statistic would be. So 0.031 is going to be somewhere in the middle over here. This is on the right side of my graph, so I'm going to click on right tail to help me come up with the proportion that I'm looking for. Once I click on right tail, I have to enter the value of my sample statistic in the box down here, so 0.031. And once I've entered that correctly, then I use the proportion that's in the little floating box. So this tells me that about 6.5% of the values were greater than or equal to 0.031 in my sample. Now in this case, we had a two-sided test. In a two-sided test, the p-value is going to be double the proportion that's in the floating box. We saw in StatKey that the proportion of values that were as extreme or more extreme than our 0.031 was 0.065. Now, this case, we had a two-sided test. So looking back here at my hypotheses, I know it's a two-sided test because if I look at the alternative hypothesis, it says not equals to. So if our alternative is greater than or less than, it's a one-sided test. If it says not equals to, it's a two-sided test. In a two-sided test, we take the proportion that is as or more extreme than what we got, and we double it to find the p-value. So the p-value for this two-sided test is going to be 2 times 0.065, which is equal to 0.130. All right, now we're ready to draw our conclusions. So recall from the previous slide that our p-value is equal to 0.130. Now, our rule of thumb says if p is low, HL must go, and if p is high, then we keep the guy. In this case, my p-value is high. It's higher than my alpha of 0.01, so we keep the guy, meaning that we fail to reject. So the first part of my conclusion is fail to reject H naught. The first part of my conclusion is always about the null hypothesis. The second part is always about the alternative. So my first part is fail to reject the null hypothesis. If I fail to reject the null hypothesis, that means that we do not have sufficient evidence for the alternative. So we do not have sufficient evidence that, okay, and here's where I'm just going to fill in the alternative hypothesis only in words. So if I look back here at my alternative was that the proportion of correct responses from degree holders was different than the proportion of non-degree holders who answered correctly. So I'm just going to write that out in words here. So we do not have sufficient evidence that the proportion of degree holders who would answer correctly is different from the proportion of non-degree holders who would answer correctly. And there you have it. That's how to do the homework for week 5.